In this example, the case is a little bit more realistic. So, a fuel gas comprising pure methane is burned with 15% excess air in a furnace. Remember, the excess air is required to achieve better full conversion and complete combustion. Both fuel and air enter at 25 degree. Okay, the air is wet. So actually, in our air, there's always some of the water vapor in it, which actually creates humidity. The air is wet, so the air is, another word, the air is humid, having a relative humidity of 60%. Okay, this is another information that we need to digest before we can solve this problem. Determine the efficiency of the furnace if the stack temperature is 100 degrees Celsius. So the first solution is we see that we look at the composition of the fuel and the air inlet to the furnace. So the fuel is very clear, is 100% of methane. The air, dry air, so basically dry air we can simplify it as 21 mole percentage of oxygen and 79 percentage of nitrogen. And since this is wet air, so it's also, apart from oxygen and nitrogen, air also contains some of water. So how do we know how much water is contained in an air? Okay, it is from this information of 60% relative humidity and 25% degrees Celsius and 1 atm pressure. So we go to the physical property data. So at 25 degrees Celsius, the saturated water vapor pressure is 0.032 bar. Okay, which means that the partial pressure of water in air, so P, so this is a symbol of partial pressure, is 0.6 times 0.032 bar, which is 0.016. 0.6 here coming from 60% here. Yeah, the 60% here. So the composition of water in wet air at 1 atm then become, so 0.019, which is the partial pressure of water divided by the pressure of atmospheric, which is 0.019 mole of water, okay, per 1 mole of air. So this is how we find out how much water enter together with the air to the furnace. So then we take a basis of 1 kilomole of the fuel. Then here we first, to make it easy, we write the reaction for complete combustion of the fuel of the methane here using dry air. So simple, dry air, stoichiometric. So stoichiometric basically means you follow stoichiometry. So every 1 mole of methane, you will need 2 mole of oxygen, okay? But together with 2 mole of oxygen, so remember every mole of oxygen we have 3.76 mole of nitrogen. So you bring in this amount of nitrogen together to form, this is a, we assume a full combustion. So there is no partial combustion of the fuel. So you produce a CO2 plus water plus the excess nitrogen over there. Okay, since this is stoichiometry, so it means that all of the oxygen is burned. Yeah, you feed oxygen in stoichiometry. But in the reality, if you look back into the problem, actually the water is supplied by 50% in excess. So what does this mean? So instead of here is 1 times 2, we put it 1.15, which is 15% excess. And then we rewrite the stoichiometry. You look here now, we have also oxygen in the stack gas. This is from the excess oxygen that you feed together with the fuel. And also now we have more of nitrogen. Okay, remember, it's not just excess, it's also dry. So then now we will bring in, so this is 15% of excess air with water wet. So remember that you have an M portion of the water, so you break down everything here, so you bring in the water here, so there will be an M extra amount of water plus so in the end you also have this water that come in together with the air in your stack. So we have this ratio, and we will be able to find the M. This ratio we get from previous calculation. So to continue, then we solve for M. So we find out M equal to 0.21 kilomole water in wet air. So you bring in this value into the equation. Okay, bring it here, you bring it there. Then we go for the Hess law. So first of all, delta H1 is equal to 0 because of both fuel and air enter at standard temperature. So delta H inlet equal to 0. Sometimes we write it in the equation delta H1. Delta H combustion of methane, we get it from chemical properties table. Okay, we get this value. And lastly, then we need to find out the theoretical flame temperature. Okay, here we use the average CP data, and we just guess first value of 2000. We bring it into the equation. We find out that actually if you guess 2000, you bring in all of this CP 2000, you find out the one in the table at temperature of 2000. So actually it is too small. So we need to guess a little bit lower. In that case, so let's guess 1800. So if you guess 1800, you will find out your outcome is 1822. So this error is less than 5%, so it is acceptable. Based on the TFT values, then we can calculate the furnace efficiency, which is the CP, basically this guy, this CP. Okay, or you can just cancel the two. So this is a TFT minus the temperature of the stack. Okay, divided by the TFT minus the standard temperature to obtain 95.8% of efficiency. So as the summary, so in this chapter we have learned about the furnace. We use furnace to supply high temperature heat. Remember, high temperature heat. And then to analyze the process combustion in the furnace, we come up with a term of theoretical flame temperature. It is used to represent the furnace flue gas under adiabatic condition. And then another important thing is that we use excess air to maintain a complete combustion of the fuel, and then to reduce the flame temperature to avoid the dissociation reaction. Thank you.